everyone, actually. So I'm the advisor of Ali Akin. He is my master student. So he studies about detecting driver fatigue actually by using computer vision. So the content is quite basic. So I will give the problem definition and then very short literature. Then the materials and methods, our results, and also conclusion and future studies are going to be presented at the end of the presentation. So we know that there are many traffic accidents occurs every day actually, and then that leads more than 1.2 million deaths worldwide, and daily more than 3,000 people dies because of the traffic accidents. And then of course besides the deaths that may cause very big injuries, and then this is very bad for the economies actually. And then according to the American statistics actually, that's going to that's causing 518 billion USD damage globally per year actually. And then again it is determined that 10 to 30% of the accidents worldwide are caused by drowsy drivers. So that's why detecting drowsy drivers are very important during the driving. So there are some applications, there are some regulations for the detecting drowsy drivers, and then starting from April 2021, all the cars that is produced in European Union has to have a driver fatigue detection systems. And then of course the regulations is just having a driver detection system, but the cars may use different kind of sensors. So about the sensors, there's not a kind of regulations, but the system has to be proven that it is detecting drowsy drivers. So the cars, besides the, for example, car companies, some people are using different sensors. Some of them are visual sensors. The other one is physical sensors. The visual sensors depends on the eye and the head movements actually. They are monitoring the drivers during the driving. The physical sensors also getting some measurements from the body, because before sleeping actually, or at the time of sleeping, our blood pressure changes, the oxygen in our blood changes, because the oxygen has changed actually, our heart rate decreases, and also the conductivity, the electricity conductivity of our body change. So that's why these are signs to detect the drowsiness. So for the physical measurements, people can use ECG and also EEG signals, and also they can get some temperature and measurements, and also some of the cars are using external cameras to detect the position of the cars by, for example, following the lines on the roads actually. And some also getting some measurements from their gas pedal pressure, because during the driving they may change. And also your, for example, handling the steering may change actually if you are drowsy. So that's why there are many ways to get information from the driver during driving. But of course some of them are variable ones. So for example, drivers may refuse to use these ones, but for the visual ones it is unvariable. So that's why it can be more acceptable by the drivers. So as I said before, physical features are secure actually, and also more reliable, but they requires drivers to wear that sensors. So some of them, for example, has to get the data from the head by using EEG signals, and they have to contact for the head actually. And some, for example, may get some heart activity, and also they get some during, for example, drowsiness. You can give some kind of vibrations. The steering wheel are much better, because the drivers are handling the steering wheel. But again, this has a negative effect because the drivers may hold the steering wheel at different locations. Sometimes they are using by just one hand actually. So again, for continuity, you may not get some information from the steering wheel compared to the, for example, EEG signals. For the literature, many people use, for example, EEG and EEG signals from the body and also from the steering wheel because from the steering wheel they can get some ECG signals actually. And also Hamza and his friends use EEG signals. Of course, they used different EEG sensors actually. And other systems are for the vision-based systems. It is, as I said, it is much better to detect the driver. They can track the eye and also the mouth actually. Ayşenur and his friends develop a kind of simple system run on Raspberry Pi. Actually, in that one, they are using a percentage of close of the eyes, and also they are following the eye status if it is closed or open by using DLIP library. And Mehmet and his friends also used followed the eyes if they are open or closed, and also they again followed the OpenCV and perculose measurements. But that was a very remarkable study because they have extracted a number of features, 35 features actually, and then they used Mercedes test track for this one. And then from these different measurements, they highlighted that eye reopening time actually are much better compared to the other features. So that's why today we have focused on eye blinking features, but especially we focused on eye reopening time to see the effect of detection. And there are also some brands, as I said before, using that systems actually. For example, Volkswagen using drivers for drivers fitness the drowsiness actually by using the sensors integrated to the steering wheel. Ford is, for example, is using the external cameras to detect if they are on the road or not. So our focus is to detect the driver's fatigue actually by using eye blinking behaviors. There are some facts about this one. A person blinks, we know that 10 to 15 times on average per minute. So we cannot, there is not a very fixed time for this one. It may change from people to people, from driver to driver. And also their blinking duration may change from time to time. Of course, the drowsiness may change also their blinking duration and also the number of blinks during that time. There are some challenges if you are going to use some cameras, for example. So some places you have to integrate the cameras to a car actually, but the distance of the drivers to the camera is a challenging part because the pupils even using the same car may be at different distance to the camera. If they are, for example, taller guys, for example, it may be very far away to the camera, but compared to the normal person actually. And also the physical properties of the drivers are quite important because their eye properties may change. For example, the Asian people has different eye characteristics. Some, for example, northern people has different eyes. So there are large number of eyes actually. So their ratio of the, for example, width to the length may change. So that's why the system that only depends on the eye properties may change from people to people and from their settings on the car actually. So these are the challenges that we have to handle it. So we thought that and also another thing is that if you are going to follow the eyes actually, the starting and the ending time of the blinks are quite important. So this is another challenging part to detect this part because sometimes people may look down or may look, for example, to the other directions, and then that can be regarded as a blink, but it is not a real blink actually. And also to make it driver adapted one. So our assumption is that the drivers, when they get into their cars, are awake. So I mean that they are not going to be drowsy at the initial phase of the driving. So we thought that we are going to get some characteristic of the drivers during the first 2 minutes, and then depending on that 2 minutes, we will compare the remaining, for example, measurements compared to the first 2 minutes, and then to detect if the driver is sleeping or not. So that's why that is going to make the proposed system more adaptive to the driver. So our flow is that we are going to start the driving, and then when the driving has started, we will detect the face and also the eyes accurately, and then after that one we have to get some measurement from the driver. So for the first 2 minutes, we will get some thresholds to detect the blinking. Okay, and also we will also detect the blinks and also the frequency of the blinks within 2 minutes. And then we know that if for example, the driver get into the drowsy state, their blinking frequency may change, and also and because of the blinking thresholds that we have defined within the first 2 minutes, we can detect their blinking characteristics also. And we will extract some features, then we can train and also perform our classification models actually. So to detect the face and also eyes, there are some common methods. The MediaPipe and also DLIP framework is used for this one. So MediaPipe can detect the face with 468 points. It is very good at detecting face, but it is not good at detecting eyes. So we have used actually DLIP framework to detect the eyes. The bottom image indicates the DLIP points, and the top one is the MediaPipe points actually. So the top one, again, as said, is used for detecting the face, but the bottom one is to detect the eyes actually. So that's the eyes defined by the DLIP library. So the DLIP library gives some numbers for the location of the eyes per meter, for example. These are the points that we can indicate the eyes. So by using that points, we can define an measurements eye aspect ratio. So eye aspect ratio is that the average distance of the eyes, we can say that the vertical distance compared to the horizontal distance. This is going to be an eye aspect ratio. Again, this may change from people to people, as I said before. And also because of the two eyes, we can get an average of the eye aspect ratio, and then that one is going to give us the instantaneous mean ear aspect ratio. So by using that one, ear actually, we can decide the blinking of the eyes actually, because at the time of blinking, eye aspect ratio is going to be decreased, because the blinkings, the eyes is going to be closed. So that's why while the distance between P1 and P4 is not going to change, but the distance between P2 and P6 is going to decrease. So that's why at the time of blinking, when the blinking starts, ear aspect ratio decreases. When for example, blinking ends, that one increases. So, but as I said before, during the first 2 minutes, we are screening, we are monitoring the people, and then because our image has 3600 frames within 2 minutes, so we get an average of this one. So ear aspect ratio for the first 2 minutes, and then from this one we also define some parameters for key to detect two threshold values. Again, the first threshold value is this one, and then that one is high threshold values. Again, that one is depend on the first 2 minutes statistics of the people. So again, to understand to define the optimal K, so we made some kind of experimental studies. So we get some videos. We obtained, for example, the 13 videos, randomly selected 13 videos, and then use different values of K to detect the blinking. So and we observed that when key is, for example, 17%, we mostly detect the blinks. So that's why we fix that value and then use that one for all the pupils. So that one is the eye features, as I said. So that's one just for an just one demonstration. So thought that this one is an eye aspect ratio, okay, and that one is the frames. So ideally, actually, this is our high threshold, that one's our low threshold, and then we thought that when the, for example, eye aspect ratio decreases, gets down from the high threshold, so that means the blinking starts, right? The eye starts closing, and then after that one, okay, if the, for example, this one again removes from that one, again, that means that the eyes has opened in that cases, because even we trust on deep features, it's a noise detection at the same time. So that's why that's a flicker diagrams. So that one is for just demonstration. That one is the real one. So that is, for example, obtained from a person's video, driver's video. As you see, the eye aspect ratio changes from time to for every frame actually, and then these are our threshold. As you see, the blinks in that case starts from that position, from that frame. So again, that is lower than the low threshold. That's very nice, because that means the eye has totally closed, and then that means eye is starting to open again, and then this is the point of the opening. So and then so that's why these thresholds, high and low thresholds, are driver specific. So that's why driver specific we have obtained from the first 2 minutes. Very good. So and then as you see, the red ones are the closed eyes, the green ones are the open eyes regions. So and then we get a cycle of the blinks, starting from the, for example, end of the blinks till the end of the other blink. So the first this duration, which is the blink close times, and also the opening times before a click, is called a cycle. So we get a feature, we get some features for every click cycles, blink cycles actually, including the open times. So we get a Utah RLDD data set for this one. In that data set, there are they obtained some 3 different videos from 60 different people actually, and then as you see, the people has 3 states. They measured that one from the same camera. That's the top one is the awake one, the second one is semi-sleeping times, and then the bottom one is the drowsy videos actually. So our system is to detect these ones. That one, the semi one, this at the middle one is not because that one is defined as semi-drowsy. So we ignored this one, and then we only focused on the top and the bottom one. So these are the features we obtained from the users. For example, the number of frames in open eye region. So that means that one is actually the duration of the open eye actually, and minimum ear in the open eye region, and then the maximum ear in the open eye region, the average ear same time actually, and also the difference from the reference open eye average actually. Again, we know that we know also the number of frames in the open eye region within first 2 minutes, and then we get the difference from this one. So as you see, we also get some measurement randomly from the randomly selected 2 blinks. Okay, and these are the measurements we get. We also repeated the same thing for the closed eye region. As you see, this part, the red part actually. So we also counted the number of frames here because that's going to give the duration of the blinking, right? And also the minimum ear aspect ratio in the closed eye region, and also the maximum one, the average one, also the difference from the first 2 minutes. In addition, so the first 10 features are called as blink cent 1. And in addition, as I said before, we are focusing on also not only the duration of the blinks, we also focus on the opening time. When, for example, eye has been closed totally, and then the time from to total close to the opening time. So that's why from open state to full closed state is another feature, and from full closed state to open state another feature, and also we get the distance. So we also try to understand the contribution of the last 3 features for the drowsy detection. So that's why whole data set is called as Blinkcent 2, but the data set with only 10 features is called as Blinkcent 1 to make the comparison. We use standard classical machine learning algorithms, SVM, KNN, logistic regression, decision tree, and random forest for this one. And then we get accuracy and F1 score for these guys. And then we obtained that the random forest is giving the highest accuracy and F1 score for the Blinkcent 1. As you see, we get very promising results. When we add the last 3 features, as I said before, the opening time, we get very nice improvement in the accuracy and F1 score for all the classifiers. Okay. Again, the random forest is giving us very accurate result, especially 98% accurate results. And as I forgot to say that we perform 5-fold cross-validation to get these results. So on the same data set, there are some other studies that get very good results actually. For example, the Chand and Kayan, actually they get a 93 accuracy, and Fan and his friends get 97 accuracy, and then our work is getting much better accuracy if we add eye reopening times actually on the data set. Yeah, so our results, we can say that yes, by using on the eye detection, by using on the visual cameras, we can get very accurate driver fatigue detection system. But if we personalize this one, if we propose an adaptive feature extraction step for this one. So in the future works actually. So we will test this system on different driver groups to get the very reliable output actually. And then we will test the results by using sunglasses, because this may also be a challenging task. So, and also I forgot the last one. Okay, so in that one we will also want to combine head movement, because if the users use some sunglasses and also normal or optical glasses, because of the reflections, we cannot, sometimes the algorithms may not be good at detecting the eye properties. So in that cases, the head also may give very good results for this one, because we know that during the drowsy times, the head may fall down and also and stay there for a long time, and also their head movement may change actually. Okay. Yes, these are the references, and then I thank you for your attention. And then if you have any question, I can get it.